Welcome back to Track 1, Part 2, Kodiak Room, Battles in Silicon, with the talk that the cab specifically picked just because of its creative use of capital letters and the number 0. We welcome Nick and Cristofaro to talk about rooting the kernel.
Thank you very much. Welcome, everybody. My name is Nick Timmers, and this is Cristofaro Moenen, and we're here to present a talk that we named Routing the Unexploitable using hardware fault injection. I'm a security analyst at Riskier, where I test the security of sorts of technologies and devices, and both using hardware attacks and more common software attacks. Cristofaro is a former colleague of mine, and he's now a product security consultant at PulseSec, and we're doing this presentation together. And before we start, who knows or who thinks to understand what I mean with fault injection? Can maybe see some hands? So for the people that do not raise their hands, don't worry, we will introduce the concepts initially before we go into the actual content of the talk. So when we talk about fault injection, we talk about changing the intended behavior of a target using faults. For example, if you look at this code snippet, which is used to open a door based on the validity of a key, using fault injection, it is possible to change the intended behavior of this conditional statement in order to open this door with an incorrect key. And this makes you wonder, how can we introduce those faults? Well, there's a whole bunch of different fault injection techniques that you can use in order to accomplish this. Of which here 4 are shown on these slides. Those are the 4 most common ones. And they have all something in common, and is that they introduce a controlled environmental change into the target in order to change its intended behavior. And what they actually do is they leverage a vulnerability that's embedded inside the targets that we're talking about. One thing to realize is that all these fault injection techniques have their own purpose, so they have also their own characteristics. For example, electromagnetic fault injection and laser fault injection have a localized nature, so it's probably possible to change only parts of the chip, whereas that does not hold up for the other 2. For all the experiments that we address in this talk, they're done using voltage fault injection. So we affect the voltage supplied to a target. But please note that similar results can be achieved using the other fault injection techniques as well. So whatever we're going to talk about in this presentation is not only applicable for voltage fault injection, but also holds up for the other ones. So we will introduce a few terms to get you up to speed. So whenever we're talking about glitches, we're talking about the environmental change. So this can be a laser pulse or a voltage glitch. And these glitches actually can trigger the vulnerabilities embedded in the chips we are talking about. And the vulnerability here is a little bit different than a software vulnerability. It's really the sensitiveness or the susceptibility of a given hardware subsystem to a particular fault injection technique. And of course focus on the fact that it has an impact on the security that's implemented in that particular chip. So these vulnerabilities are embedded in the hardware, and it's very difficult from a design to see if this vulnerability is applicable or not. So it's very different than for software vulnerabilities, where you can look at the source code and actually identify that it's there. In order to figure out if these vulnerabilities exist in chips, you really need to perform the actual attack or do something similar like a characterization phase. And also one thing to realize is that you cannot counter these vulnerabilities by hardware or by software. The only way to get rid of these vulnerabilities is to change the hardware in a way. And we'll talk about that a little bit more later. And the key point about this is that by injecting these glitches, triggering these vulnerabilities, we can create faults. And these faults are the unintended behavioral change in the target. So these things happen at a specific moment in time, because these glitches are time-based. So we inject them at moment A. But it doesn't mean that these glitches are not happening, or these faults are not present anymore at moment B. It can be, so some faults are temporary, some are persistent, and some are semi-persistent. And semi-persistent meaning that if you reset the entire board or the entire chip, then the fault is gone again, and you need to inject a new glitch in order to introduce that fault again. But the key point here is that faults can be mitigated using software. For example, if something goes wrong, you can execute software at a later stage in order to detect it or counter it. And we'll talk about that a little bit more later as well. So what do we need to glitch? Well, you do not really need anything to glitch if you have time and you're very lucky. Because a long time ago already researchers and engineers alike figured out that influences from space actually have an impact on the data stored in computer chips, so-called cosmic rays. And in similar fashion, the alpha decay from radioactive material actually also had an impact on the data stored in computer chips. And of course, this does not provide a lot of control, and it's very tricky to generate a cosmic ray out of nothing or to wait for it to arrive. So since then, a lot of initiatives are made to make high-end tooling that allows you to perform fault injection techniques. And for example, the company that I work for, Riskier, actually creates this type of tooling. And we have a wide range of different tools to perform different types of fault injection techniques. And they provide flexibility, speed, precision. And all this high control is very nice for labs that want to do these attacks on a regular basis on different targets to set benchmarks and so forth. But of course, these tools are very expensive, and your typical ethic hacker will not have access to these tools. Basically, the budget for these guys and girls is actually not large enough to buy a laser and put it in their attic. So luckily, there's other options to perform fault injection, and that's what you typically see in the field. Whether you use open source initiatives like the Chip Whisperer Lite, whether you use very cheap microcontrollers or FPGA boards, they all are capable to introduce those glitches. And they range from, let's say, 30 euros to a couple hundred euros. Same thing for dollars, actually. But before we actually dive into the fault injection we are talking about, we like to take one step back and maybe wonder, do we really need tooling to introduce glitches into a target? Well, we've seen recently that this is not the case. Well, there's something we call software-activated fault injection, and that is possible whenever you can use whenever you can use software in order to trigger the vulnerabilities inside a chip. And please note, even though these vulnerabilities are triggered and driven by software, they're still happening inside the hardware of the chip. So some recent examples where this was the case is, for example, the Rowhammer, and most of you are probably familiar with this, where it was possible to flip bits in the DRAM chip by reading out a neighboring memory address. And the point here is that the vulnerability that we're talking about, so the fault injection vulnerability, is actually in the DRAM chip, but triggered by software. And very similar, recently a paper came out where the author actually showed that by setting up a certain functionality of ARM, the so-called digital voltage frequency scaling functionality, it was possible to operate the chip out of its specifications. So we all know chips have specifications. If you run them out of there, they either don't work or they start misbehaving. And this misbehavior is exactly what caused similar faults as what we are talking about when we perform glitches using hardware tooling. And this, for both attacks, it was possible to generate malicious signatures and actually change instructions as well. And the key point here is that what we are talking about is not possible to do it remotely. But if it's driven by software, you can actually do this remotely because you can get control over the device remotely first and then instruct the hardware to start misbehaving. So I would like to introduce some real-world examples what we are talking about. And one thing that I would like to touch upon first is what the academia typically is talking about, what can go wrong. So there's two types. So we can affect the control flow of a program, so we affect the software, or we can affect the data that the software is working on. And both of these concepts actually are used to envision different types of attacks and envision what kind of countermeasures are needed in order to mitigate these attacks. So the academia is always very focused on cryptographic attacks, and it's very nice. And one subclass of these attacks is actual differential fault analysis. And this is a very powerful attack in order to get keys out of a device. So the idea is, for example, for the RSA-CRT algorithm, we compute a valid signature, we store that signature, and then we generate the signature again. We inject a fault, which makes the control flow or the data of that computation go wrong, which results in a corrupted signature, but still created with the same private key. And then by using some mathematical magic, we can actually recover the private key using those two signatures. And please be aware that this type of attacks actually apply to most other cryptographic algorithms, including symmetric algorithms like AES and DES. A very interesting attack by an author that was looking into the security of the Xbox, maybe you're familiar with this, is he figured out by injecting a small pulse in the reset line, it was possible to only reset the chip partially. And this actually allowed to reset the CPU's registers while it was doing a mem compare without affecting the continuation of the chip. And this allowed the person that was looking into it in order to bypass the integrity checks performed during boot, which allowed arbitrary code execution. In similar fashion, the guys looking into Nintendo figured out that by injecting a glitch, it is possible to bypass a length check that was used during boot that guaranteed that an image that was loaded in was not too large. And by bypassing this check, it also resulted actually in code execution and the asset that they were interested in, the key that was only accessible using that moment in time. Also recently, two researchers actually created their own electromagnetic fault injection setup to bypass secure boot of a Cisco phone. And the interesting part here is that a very nice characteristic of electromagnetic fault injection is that you can do it from a small distance. So they were able to do this without opening the casing of the phone itself. So what we've seen is that the equipment and the knowledge to perform fault injection is actually becoming available to the masses. So we see much more content being generated online, on YouTube, on Twitch, on whatever platform where people are experimenting about fault injection. And another trend that we've recently seen is that it's not always needed to have special tooling to perform fault injection. We've seen now that it's even possible to do it in a remote fashion. It's very interesting. So what can we do in order to mitigate these attacks? Well, the academia typically splits up the fault injection countermeasures in two groups. There's the so-called hardware-based fault injection countermeasures and the software-based countermeasures. The hardware-based countermeasures are really the strong ones. The idea there is that you create a chip and you implement specially crafted hardware in order to prevent these type of attacks. And then typically they focus on redundancy and detection. And whenever there's detection, because the hardware is specially crafted to do this, the detection will be very close to the moment the glitch is injected. And also, it may be possible to actually prevent the injection as a whole. For example, if you want to shoot with a laser on a chip and you cover this with a shield, it's not possible anymore. However, we must realize that the standard embedded technology of today, so that is all the chips that you find in your phone, in your most STBs and other equipment, will not have these features implemented. And whether that is because it's expensive or very difficult to do, we do not know exactly. So most of the things we're talking about actually are not prevented using hardware-based countermeasures. The software-based countermeasures, actually, you can be as creative as you want. There can be computational checks, redundancy. For example, if there's one critical point and you can bypass that using a glitch, you introduce a double check. So there's two checks, which results that you need probably two glitches to perform this same attack. And the key point here is that software-based countermeasures do not prevent the injection itself, but they mitigate the fact that the vulnerability results in a fault, so you mitigate the fault. For both, it is important to realize that they do not prevent injection as a whole. So it is very unlikely that a chip is not affected by any of the different fault injection techniques that are out there. But they definitely are capable of lowering the probability for successful attack. And that's, as a defender against attackers, that's what you're looking for. You want to make it as complicated enough that the attacker does not succeed, even though in theory the attack might still be possible. I would like to emphasize a little bit more on the software countermeasures because that's important for the rest of the presentation. We know now they do not prevent fault injection, but they increase the attack complexity. But the key point here is that if you want to counter something by software, this software needs to be executed. So from the moment you inject the glitch, you need to wait some time, or there need to be some room for this software to be executed in order to be effective. And also, software typically affects only a small part. So for example, if you use the same example as the check, if you have to implement two checks, the second check only protects that specific check. But for example, in the code base, there will be a lot of checks. There will be a lot of critical points. So all these critical points need to be targeted specifically. And whether those are crypto operations, data integrity, critical decision points, it does not matter. If you want to make this work for a given code base, you need to implement it everywhere. Otherwise, the attacker just goes for the code where it's not implemented. So one question I would like to give you, and please keep that in the back of your mind, because you will be able to answer this at the end of the talk, is that are software fault countermeasures sufficient to protect targets? That's something we want you to think about. So most of the examples I've shown, whether that's for the Xbox, for the Nintendo, or for the Cisco phone, they all target the devices during boot using fault injection, which in a way makes sense because these code bases are typically small and it's not guaranteed that there's vulnerabilities there that you can leverage in order to bypass the security. But this makes me think, why don't we use fault injection during runtime? And that's exactly when fault injection met Linux, and that's basically the foundation of this presentation. So Linux, as you all know, and like any other operating system, because these attacks are probably not specific for Linux only. They are probably apply in a slightly different fashion for other operating systems as well, is that operating systems are attacked using software exploits. So if you look at the last 3 years, there's numerous different CVEs that all apply to certain vulnerabilities that range from denial of services to privilege escalations, for example. However, the point is, what if the vulnerabilities are not there? So what if you have a fully patched operating system? And finding vulnerability in a fully patched operating system is very difficult. Of course, you can always go to a company that have these on the shelf, but then you need to pay a lot of money for them. So others came to the same conclusion. So this is a quote from the guys looking into the Nintendos. How can you exploit something that has no bugs? It's not possible, right? Well, what if you can introduce your own bugs? And this is exactly what fault injection can do. We can introduce our own bugs. So in order to do fault injection, you need a setup. So like I said already, we are actually performing voltage fault injection. So this is a simplified version of the setup we use. So we have a workstation that communicates with a glitcher, the yellow box here. And it communicates via serial interface with our target. And our target in this case is a Xilinx board that houses a fast and feature-rich system on chip. And inside this system on chip there's a ARM Cortex-A9 subsystem, which is actually executing our operating system. In this case this is Ubuntu. And there is 3 signals that are essential for fault injection. First of all, we're doing voltage fault injection. So we have to apply our own voltage signal to the target. And in this case, we're not targeting the entire PCB or the entire chip. We're only powering the actual power plane, because typically on a SOC there's multiple power planes. We're only powering the power plane that's responsible for powering the ARM cores. And then whenever we inject glitches, then sometimes the target will enter an erroneous state and we want to reset the device in a known state. So we have a reset line that actually allows us to do this. And then there's one signal originating from the target itself, and that's actually a trigger signal. So typically that is a GPIO pin that tells our glitcher, okay, from now on you need to get ready. We want you to inject a glitch anytime soon. Please note that it does not necessarily have to be a GPIO pin. It can be also any other signal that originates from the target that is related to the point in time where you want to glitch. Typically, a setup looks something like this. So it's really the nitty-gritty hardware hacking. There's cables everywhere. There's probes. There's things soldered on and off, and I don't know what. This is a typical setup for voltage fault injection. Of course, it depends a bit on the person how neatly this looks, but this is mine. So for all fault injection techniques, we need to take care of a bunch of parameters, and this will be different for the different fault injection techniques. So the green line here denotes actually the trigger signal. So it tells our glitcher, okay, get ready, and you're done. And basically between those 2 moments in time, there is the operation that we want to affect. And then the red line is the actual voltage signal. And the first parameter we have to take care of, the time we wait between the moment the trigger signal goes up and we inject the glitch. That's the glitch delay. And we want to randomize this within the window, because we do not know exactly where that moment in time is, where that operation is happening. We only know that it's between the 2 green edges. And then we need to figure out how long the glitch will be. So that's the glitch length, that's parameter 2. And then we need to figure out the amplitude of the glitch. So that is parameter 3. So what we typically do is, in order to figure out both what parameters are effective and if the target is vulnerable, we write a very simple program. The only thing it does is it sets that trigger signal high, increases the counter, sets the trigger signal low, and sets the counter back. And the idea here is that if the counter value is actually different, then somehow we change the intended behavior of this program. And it gives us enough confidence that we can move on to the next step, actually targeting something useful. So whenever we execute this program and we inject the glitches within the two trigger edges, we expect different types of outputs. So whenever the counter value is as expected, then the injected glitch has no impact. Whenever the counter value is not being sent back at all, then the glitch is probably too hard and the program cannot continue. The target either resets or something else goes wrong inside the chip. And whenever the counter value is actually different than the intended value, then we know that somehow we affected the actual program. And we do not know what goes wrong, but we at least know something goes wrong. And this might actually allow us to perform an actual attack. So what we typically do is we randomize all the parameters we had. So we have three parameters. And what we see here is that we have on the left side the glitch VCC, and on the bottom side we have the glitch length. And all these experiments are plotted. So on the top left side, we actually see a green area. And this is where the glitch VCC, so the glitch voltage, and the glitch length have a combination that did not have any impact on the program whatsoever. And on the bottom right, we see yellow area. So those are the mutes. And these are the experiments where the combination between glitch length and glitch VCC actually resulted in a glitch shape that was too strong. So the target did not continue anymore after the glitch was injected. But between those two areas, we see the so-called sweet spot. That's the red trend that you see there. And those combinations actually resulted in the program to misbehave, but continue, because it allowed us to actually continue after. So we could generate a new experiment directly after. So what this shows is that there's some sort of relationship between the glitch voltage and the glitch length. And this provides us also enough confidence that we can fix one of those parameters in order to minimize the parameter search space for the actual parameters. And also this provides us enough confidence to go to the next step. And that's actually attacking Linux. And this is the moment I give the presenter to Christopher.
Thank you, Nick. Nice to be here. Thank you. Well, Nick has presented more or less how we do fault injection, what is needed before, what is also the physics involved. Basically, you are, in case of voltage, you are subtracting energy to a target, either to a level which you are not able to affect it, which is basically the green, or you are shutting it down with the yellow, or you are in that sweet spot where something happens. We don't know basically yet, but what? But that might be useful and usable for an attack. And this is exactly what we want to use and we are going to use for attacking Linux. So let's imagine a situation where we have a program running in user space, and we don't have the privilege of doing anything at kernel level. We might want to use these fault injection techniques in order to make the code misbehave in a kernel space so that our user space application gets much more privileges than intended. So basically what we are seeing there is that a user space application that makes a system call just for activating some kernel code. And it should not be allowed to do something, but by using our fault injection, we attempt to make that misbehave enough so that that security check is bypassed and gone. So this is the general idea of this situation. You don't need privileges in order to do this attack. You just need to be able to make some kernel calls and be able to interact with the target. This is what we are going to do now. So let's figure out for one moment the memory mapping, how it works in Linux. So you have a devmem, a device. Normally this device cannot be opened by a user space application. The reason is that this device allows to map any part of the physical memory into the user space application. So this means that if you are able to call that from user space, you are also able to map kernel memory, physical space, kernel memory pages within your application or user space program. And this means that you can either read it, you can either modify it, because then you have the privilege for doing that. So of course there are some security checks there that are performed at the kernel level, like, hey, you are user space, you're asking me to open devmem, no way, you are not allowed to do that. If you are a root application with root privileges, in a way, you are allowed to do that. So there is a check somewhere. There is some point in the kernel that says, if you are user space or if you are kernel. So there is one point specific that makes the check. What if we are able to pinpoint exactly that check, and then at that point we are able to make the program misbehave and go into the wrong path? So the goal would be then we try to open that from user space many times. We try to bypass the check performed by the Linux kernel using a glitch at that point in time. And then, if we are lucky, we are able to map arbitrary physical memory in user space. So the plan is that we actually make the system call, we try to glitch there, and if we have a good attack, that means that we have full kernel memory access from user space. And let's see what happened. We are going to use basically this call. This is very simple. As you can see, basically you see the trigger high and trigger low. This means that between trigger high and trigger low, when we actually do the open, is exactly the point in time where we're going to shoot our glitch or try to inject it. Because that's exactly the point in time where it's likely that those checks are performed. And if we are able to inject there at that point in time, then we know that we might be able to perhaps bypass the target. So basically this code running in user space, and we continuous call sys open on devmem. And this is what happened basically. What you see there is that the green, this is a combination of glitch length and glitch delay. Glitch delay means that we have the trigger and we have some point in time where we actually shoot. This is randomized. More or less, sooner or later, we are going to hit something that might have an effect. And then the glitch length is that how much energy do we subtract from the target. These are things that we don't know, of course, but by having a statistical approach, we know that out of, let's say, n parameters or n attempts, we might have at least one success. And as we usually say in the fault injection field, one is enough. And what we are going to see here is that every green there is that means that the target has not been affected, so we have not been allowed to open the device. Those small yellow up there, you are going to see that the target has been reset, but what's interesting there is that the red ones are successful experiment where we have been able to map in a user space application kernel space. So this, every red there is actually a successful attack over there. So we actually performed 22,000 experiments in 17 hours. Just one day, more or less. We went for a beer, we went out, and this was just running. So we identified that during that specific moment in time, so from the trigger, there is a window like 25.5 microseconds from the trigger. So when you say, hey, open, and up to 27.8, there something nice happens with that percentage, which may be very small, but in practice means that every 10 minutes, we are able to map that kernel space within the user space application. And keep in mind that the kernel is fully patched. There is no vulnerability which is known. We don't need it. Even if it's there, we actually don't need it. This means that once the setup is running, in 10 minutes, we get kernel memory into user space. Second one, now we want to, rather than doing that, we want to escalate. We are still user space. Well, we can do a lot in that case, but we would like to see our nice dash at the end of the shell. So what do we do there? Okay, keep in mind that when you actually do a call to a function, there is always a result which is returned to the caller, like yes, true, or no, false, or something like that. This is usually represented with some binary value in the assembly, in the call. So this means that we thought, perhaps if we actually set all the registers to this good value, we might have a situation that this value is actually returned to the caller by our glitch. We don't know how. So it would not be possible for us to say, hey, in this code we were able to. But we are able to say that statistically we have been able to affect that. So we first set all the registers to 0 before. So before we are doing our system call, which is this one, they say, hey, I want to set all my user ID, all my ID internally to 0, which is representative of the root ID in Linux. So if we're able to get this 0 from the register down to the writing into the user, into the privileges or into the identifier of the user, then basically we're done. Because at that point there will always be a check. Hey, you're not allowed to set yourself to root, because what we are doing with that system call, hey, I want to set myself to root. Now I am root. This is something that only root can do, and the user space application cannot do. But this means that at some point, again, there is a check. You will be not allowed to do that, and if we are able to bypass the check, then we are going to execute a shell with system function. So the plan is, okay, call that system, make the system call, then glitch during that time of system call, trying to hit the check that we are actually seeing. And if we are able to see, in a successful experiment, if we are able to see the dash at the end, this means that we are going to be successful. Again, this is the code that we are going to use. As you can see that all the registers are set to 0, basically. You said in the ASM volatile part, there is a trigger high, say, hey, I'm going to start. Then there is a trigger low when we actually made the system call. And at the end, you say, if the return value of the system call is 0, which is exactly what we want, then we call system for spawning a shell. If everything has worked correctly, then our user ID has been set to 0, and this shell will be spawned as root while we are not root initially. So this is actually the experiment that we see. Again, green is not happening, nothing is happening. Yellow is a reset. But what is interesting is that those red points are always successful experiments. So for each of those red points, we have been able to get a root shell out from a user space application only by calling, hey, set me to root, and bypassing the check at that point in time. What is interesting here is that basically, we did this amount of experiment in 21 hours. We see that within the window of time, there is a quite 1.3% of experiment. So if we set the glitch delay once we have found out there, we know that basically in 5 minutes we are going to get a root shell, even without a vulnerability. What is interesting here is that you don't have a specific point in time. So the red points are actually spread across a larger window. So this means that the number of checks are probably happening at a different point in time. And if you actually change one of them or any of them, like let's say a parent calling check this point, or then a child being called and check this privilege and all these things. So there may be multiple points in time in the code where we actually are able to modify the return value to 0, likely, and then set this, our ID to root. So basically, the summary here is that we have a security boundary bypass. So you have a user space application which is able to acquire or perform action at the kernel privilege level, which means here is we get both full access to kernel memory and also execution of root shell. So this is not dependent on software vulnerabilities. I mean, this will work any point in time, anytime, regardless of the existing vulnerability in the software, because as Nick was explaining, the vulnerability lies in the hardware. And we are able to use the faults, so the changes in the actual execution in the data or in the software, to our own advantages. Even if we don't know in advance what things we are going to change, but statistically, so every 5 or 10 minutes, we get something like that, which is useful for the attack. It's important to realize that this kind of attacks focuses on a specific point in time, on targets, where there is a check, then you want to shoot at it in order to see if you can actually change that behavior. And this has been a very, let's say, used attacks also during secure boot, also in academia. This is a model which has been used. The fact that if you have a check at some point, you might want to duplicate that so that I need to shoot at 2 checks. So it is more difficult. But in our case, basically, we don't even need the source code, because we don't know even which check are we actually bypassing, because we are approaching that statistically. You just call, you make a number of experiments, and after some amount of time, which in our case was 5 or 10 minutes, we just get to exactly what we want. So we don't need the source code for that. Although when you actually analyze the code for looking at these checks, you make consideration that specific point in time. But from an actional point of view, from an operational point of view, you don't need the source code. So basically, as I was saying, the traditional software countermeasure do apply. Because if you duplicate or triplicate the check, then you have to be much more lucky, much luckier in order to hit those things at the point in time. Especially if you actually randomize them, then it becomes even more difficult for me to attack this. So all the consideration that Nick was making before actually fully apply, because we need to target one point specific in time. But there is something more here. And we think that could be really interesting also for this kind of attacks. But let's go one step back. So usually, you don't know what happens. So in order to research about fault injection, you do a model. It's called the fault model. For example, we assume that this fault might allow you to skip instruction, such as you have an if or a check, and you actually skip the instruction, not executing it. Or you might have a situation where your fault model says, hey, perhaps this fault injection technique allowed me to flip some bit rather than skipping instruction. So this means that you have a way of, you start with a model with something that you think that might happen, and then you use this model in order to envision your attacks. Like, okay, if this is what happens at the fault level, how can I use it for attacking things? If I think that my attack is making instruction skipping, then perhaps I could look in the source code where there is a check, time where this check is performed, and shoot. If I think that my attacker instead attack is able to flip bits, perhaps I might flip data, or I might change cryptographic keys or cryptographic material. So this means that your fault model actually drives you or guides you in what kind of attacks you want to perform. So you have a fault model, you think of attacks. If you think of attacks, then you start thinking about countermeasure for counteracting the attacks. So basically, the fault model guides you into attack and in countermeasure. The problem is that if you don't have a model, it might have not been researched yet. And the point that we are going to describe here is that we have a new fault model. Instead of thinking of instruction skipping and bit flipping, we think of instruction corruption. So that you have an instruction, a normal one, basically, where you actually flip bits and you modify the instruction, the actual instruction which has been executed. You see those examples, for example, for MIPS, where one bit flip make the addition goes from adding 8 to the register T1 to adding 0 to T1. So if in our attack we are able to flip that bit, then the instruction actually changes, the one which is executed. Of course, we don't know. We cannot control how many bits are flipped. So even in case of ARM, it might be also possible that multiple bits are flipped, and instead of having a modification on the operand, you actually really change the instruction. So instead of having a load, it will turn into a store. Again, we don't know, but in our modeling, we think that these things may happen. So we have limited control of which bits will be actually corrupted. But still, these may become useful. If you start thinking about, okay, you have an instruction, but I can modify it, then many things can happen. Keep in mind that this approach, this fault model, also includes the other models we have been discussing. For example, instruction skipping is where you turn the instruction into something that basically does nothing else, does not affect the system, and just goes to the next one. So this fault model also includes the other one. So at this point, we can use this fault model for envision a new attack, which is controlling directly the program counter, because until this point, we've been just focusing on checks. No, I want to have PC control. Experiment, in this case, on the ARM32. That has an interesting instruction architecture. In ARM32, PC is a register like the others. You can address it directly. So as you can see, basically, any instruction there has a destination register, they are on the left, basically, which can be potentially corrupted so that, for example, the first move from R1 to R7 moves the value from R1 to program counter. So this means that what was there in R1 goes directly into the program counter, and the next instruction is executed from that address. So this means that if you are able to flip that bit, what goes in one register goes directly into PC, and your control flow is completely gone. Same goes for the other instructions. These are still examples, and depends how many bits you can corrupt. So there are many possibilities that might lead what is into a register to go actually in PC rather than into another, in the designated register, the intended register. So you already are starting to see that with this model, we can envision attacks where the program counter is completely set to the value that we want if we are able to set those registers. Of course, the objection could be, well, the program counter is accessible only in ARM32. Yes, but we both know that having control of the stack pointer is basically the same nowadays. If you get control of that, then there are a bunch of techniques. So this means that this model might be effective. While we demonstrate that only in PC, we can be effective also in many other architectures and not only ARM. So what we are going to do, we set all the registers to a specific value before doing our call, because that's, for example, that address. Then we execute random system call, and we shoot a glitch in order that that value goes into the program counter. And if we are fine with that, we are going to have the control flow hijacked. This is the code that you see. The initialization that before was done with 0 now is done with the address that we want to reach. And at some point, we just say, OK, we don't know which system call. We call all of them randomly. But we found out that some are more resilient into producing faults. And then we actually focused mostly on them, which does not mean that the other ones are not vulnerable, just that this one yielded more results, better results. Again, what you see, green, not interesting, as well as yellow. But every point in time, every point, a red point there, is a situation where we have been able to get control of the program counter fully. Remarks, we made this 12K experiment in 14 hours. The real point is that we gain control of kernel space program counter every 10 minutes, which can be quite interesting. We are going to have a video demonstration now.
Well, at least this time we don't have to worry about the demo not working. So basically this video shows the setup that we usually bring along. Unfortunately, we don't have it this time. As you can see, it's the same setup as I showed before, but it's a bit more neat. So important part is that this is the actual target where we inject the glitches, and we solder our glitching equipment directly on the PCB because you want to keep the cables as short as possible. The other things that were shown before are just some things to reset the target or to communicate with the target. They're not that important. After the talk, we can talk a little bit more about how we create these setups. This is just an oscilloscope that provides us some feedback about the trigger and the moment we inject the glitch. And now we hover to our little workstation. And basically we control the glitcher and the target from Python. It's quite convenient and quite flexible. And the idea here is that we are first going to reset the target into a known state. And you see that happening now. So these numbers, they actually denote the things that are printed during boot on the serial interface. And after it's fully booted, it will take a while, let's say 30 seconds. We actually start the experiments. And what we're actually doing here is we'll wait until it drops into a reset. So to quickly introduce what's going on here. So this is just whatever you would type in Linux. So this is the Linux shell. And then this is some metadata of the experiment. So the experiment number, the length of the glitch, the moment in time the glitch, and the glitch VCC, so the glitch voltage. We fix both the length and the moment in time the glitch because it generates good results. And we only slightly increase the glitch voltage. And then what we'll see happening so whenever we're lucky, something special will happen. And one of the things that can happen is something like this. Wait a little bit. So what we see here is that something went wrong. Somehow an exception got thrown. But what we see is that the PC is set to 0, which by itself is interesting. We see the residue of the special address in the registers. And we actually see, I'm not sure where it is, here that we are in kernel mode. And if we're very lucky, we actually get what we're looking for. And I will move a little bit forward. So we see another exception, another exception, another exception, another exception, and then boom, and this is what we're looking for, is that you can see that the PC counter, the PC register is actually set to the actual value, the residue is still there, and we see that we're in kernel mode. So this is successfully hijacking the control flow once the kernel is executing.
Yeah, so you've seen the video is less than 5 minutes long. So this is actually a real experiment that we actually just went. And in 5 minutes, we got the PC set to whatever we want. So the summary is that we got, again, a security boundary bypass, but this time we had code execution. And this is really the interesting part. The reason is that before, let's say, the previous models focused on bypassing checks or flipping bits. And this is the first fault model that instead allows you to use fault injection for directly gain code execution. Again, not depend on software vulnerabilities. And what is really interesting here is that any instruction can be a target. You don't need to have a check to target for your fault. Any instruction can be vulnerable or can allow you to use the vulnerability in the hardware. And this makes things quite different, which makes this attack quite so special, because first, you need just win one successful fault, and then you get control. You get kernel-level control, and you bypass the security boundaries. In our case, it was 10 minutes, 5 or 10 minutes. It is global, because you don't need to protect one instruction. It's basically the full instruction space and execution that needs to be protected, and this makes this very difficult to protect against this attack. Because any instruction that can be executed as soon as you change the destination register, either to stack pointer or the program counter, and that's already already game over. Well, the software control is achieved immediately. It's not that basically there is some step in between. That one immediately gives you control from that glitch point in time. You load whatever you want from the register, and they will go exactly in the register that you want. It's powerful because it works across security boundaries, and it's unpredictable. Basically, we are creating execution primitives out of thin air. So we have a data primitive, like a load or a store, that will be turned into an execution primitive just because the destination register now is program counter or SP. And this is something which we think is really innovative in what we are doing now. The impact is that the hardware fault injection countermeasures are fully applicable, so they work. If you're able to prevent the glitch being injected, fine. But the software countermeasures are likely not executed because they're executed after the glitch. But we get control of the software immediately, so they are not executed, but completely bypassed. And even if you protect one piece of code, we have also the other instructions that are running before that can be targeted. And this makes that also difficult. So the traditional software countermeasures are ineffective. But what may work is something that you actually know very well, which are exploit mitigation. The one that actually limits the usage of an hijacked control flow. For example, ASLR or any non-executable memory or things like that. Control flow integrity, all these things that prevent the usage of a hijacked control flow, then they will work. Because we get controlled in a different way. But because we get controlled in a different way, all protection that prevent the hijacking of the PC or exploitation, the exploitation will not work. Stack cookies, for example, will not be relevant here. And not even other things that prevent the hijacking. But only that limits the hijacking, that will work. We are going to finish our presentation by saying that these attack trends from fault injection are actually reaching a wider audience. The equipment has become more accessible, research is increasing, but also the techniques that we are discussing here allow to completely subvert software security boundaries, which seems to be completely secure from a software point of view. The currently used fault injection countermeasures that are devised by the academia or in general, at least from a software point of view, the software-based ones are not effective or are mostly insufficient. And the point is that the fault injection attacks can be cheaper than a software exploit. We may arrive at a point where basically instead of spending 50K for a software kernel, for a kernel exploit, you might decide just to spend 2K and just go for it and see what happens. So the point is that if you want to improve products, start including fault injection attacks in your threat model from the start. And start working on the resistant hardware, because protecting software might be either difficult or not even possible. Tests, because that's the only way that you can find vulnerability on fault injection. You cannot by looking at source code or a design. And use strong exploit mitigation, because they will work also for this or for some class of this attack. Or take your assets and put them in only hardware or in pure hardware stuff and make that stronger, and don't rely on software. But still, that's something that we all know that is needed. So the conclusion here is that fault injection attacks are coming to the masses, and they will not go away. Then they can easily subvert all the software security models that we've been thinking and studying for long. And basically, any unprotected device is vulnerable. So factor in countermeasure from the start. If you don't have countermeasure, it is vulnerable. Assume it like that. Thank you.
So we probably only have time for like one question. So raise your hand if you want to be that one question. and here are some underscore is not a security boundary stickers for you.
Great, thank you.
Hi, thanks for giving your talk, by the way. So I just had one quick question. I'm wondering if you have any recommendations to make sure that a fault is injected at a correct time on systems which don't have trivial outputs, such as like a GPIO that goes high when you need to exploit something here.
Yeah, so that's a typical problem we're facing, because, for example, for the examples introduced in the beginning, where they target systems during boot, typically secure systems during boot don't print anything. So, and there will definitely not be a GPIO signal going up, and definitely you will not have the capabilities to actually run your own code to set these GPIO pins. So what we typically do is we look at the power consumption of the target. So we, for example, put an electromagnetic probe on top of the chip that can tell us what's going on inside the chip to a certain extent, because there will be certain patterns. And then the idea is just to find a specific pattern before the moment in time you want to have the glitch that is coupled to the actual moment you want to glitch. And then you can use specialized equipment in order to generate a trigger signal based on the power consumption. And that works actually very well. It's even better than a GPIO signal itself. Yeah, maybe because there's no time anymore for questions, if anybody has questions, we're here till Friday. Please approach us and we can discuss whatever you would like to discuss. Thanks a lot.
Round of applause.
Thank you.